Thank you. Good morning. My name is Amreesh from AFRINIC. Today I'm going to tell you a story of packets in terms of latency. Actually, the idea behind this work, it is one of the first research work we are doing at AFRINIC in terms of internet measurements and internet performance. And we wanted to know how countries are close together in Africa. Not in terms of political or geographical consideration, but mostly in terms of latency, because this is what we are interested in. So, what we know already, we know that we in Africa, if, for example, you are a network in one country and sometimes you want to reach another network in the same country or in a neighboring country, what happens is that your traffic goes outside of the continent and comes in again. Well, this doesn't look too good because this is more expensive than a direct connection. And it also adds a lot of delay to that traffic that you want to send from let's say, two neighboring networks or countries. So the issue of circuitous routes and hairpinning has been there for a while, and this is what initiatives such as deployment of IXPs is actually trying to mitigate on the continent. Our research questions were that, okay, we have seen a few deployments of IXPs in the region. Can we actually see what is the impact really? We decided to let put countries together, let cluster them together in terms of latencies and see how they are behaving when they're trying to send packets from one place to another. So to do such a measurement study we need to use measurement platforms. One very well-known one is the RIPE Atlas platform. By the way, we are distributing RIPE Atlas probes. We've got a few with us, so if you're interested to host a probe, that would be wonderful. So RIPE Atlas, as you know, is spread around the world, and we have a lot in Africa. However, we don't have as much as we would like to have a quite considerable amount of probes to do perhaps a statistically significant analysis of latency. So we decided to go with another new platform called Speed Checker. Unfortunately, it is a proprietary platform. The data is not open, so we had to pay some little amount of money to perform the measurements and also get the data. But the advantage of this platform is that it was much more spread across Africa, basically covering almost 52 countries and more than 300 AS numbers. So basically, that was giving us much more vantage points than RIPE Atlas. RIPE Atlas is good, it is reliable, because it is hardware-based, but we have a little bit of bias in Africa. For example, most of the live RIPE Atlas probes are based in South Africa, and also a lot in core networks rather than eyeball networks. So, using Speed Checker, so we had 850 probes in Africa, covering 319 AS numbers over 52 countries, so that was quite good. So basically 50% of the countries had at least 20% of their ASs probed in that study, so that was quite something. So on one side we have the vantage points, and then of course now to get delay information we need targets. So those targets were speed tests targets in different African countries. So we have 213 of them spread across 42 different countries. And what we did to get our data is just to send a bunch of pings and trace route. A lot of pings sent to randomly chosen targets, and exactly the same for trace route. And then we analyze the data. Well, of course, this study was done over 3 months. Measurements was carried out 4 times a day, giving us more than 42,000 RTT samples and more than 31,000 trace route. So basically saying that, okay, that amount of data we got is quite considerable and can actually be used, is quite representative of what's happening on the continent. So we collected everything, mashed up all the data together, and we got this very beautiful heat map of latencies. So basically, it's a matrix. So a single square is actually the latency between 2 countries. As expected, if you see the diagonal line, it's all in the same color, blue, almost. Blue being meaning very low latency, and red actually high latency. So what we are seeing, therefore, is in-country latency. So latency from a vantage point to a speed test server in the same country. The in-country latency is low for most of them, except for a few cases. For example, we have Congo DRC, where the latency is higher than 300 milliseconds. When I checked 1 or 2 weeks ago, Congo has an operational IXP, if I'm not mistaken. So it would be interesting to understand why is latency that high in the country. Well, the country is also a big country, but still, if they have an operational IXP, I would expect latency to be much lower. We calculated the mean in-country latency. In-country latency in Africa, and the mean for Africa in general is 78 milliseconds, which is very comparable to the LACNIC region. LACNIC meaning Latin America and Caribbean, 76 milliseconds. But North America and Europe are much less. So we kind of have a benchmark with North America and Europe to see where we need to head eventually in the future. I guess there is more work to be done. Here in this slide, I've actually highlighted the Southern African countries, since we are at SAFNOG. And as you see, most of the dots are blue, except a few cases. For example, Zambia and Malawi, 2 neighboring countries, but have high latency, more than 300 milliseconds. Zambia and Zimbabwe as well, Mauritius and Mozambique, high latency, and Mauritius and Réunion. That's quite funny because Mauritius and Réunion are like, what, 500 kilometers apart, connected on the same undersea cable, but still a very high latency between those 2 countries. Why is that the case? Perhaps there's no peering between them. We know that Réunion is also a French territory, serviced most probably by France, Orange. So those could be the reasons. We don't know. We need to investigate. But we also want to highlight that some countries are doing very well in terms of in-country latency, such as Mauritius, Réunion, and Côte d'Ivoire, under 30 milliseconds, and under 40, South Africa, Egypt, and Benin. So that's quite encouraging to see. Now that we have this matrix of latency in between countries, let's go for clusters. So we applied an algorithm, a clustering algorithm that is usually used on social networks to cluster algorithms that have similar characteristics. So here we clustered based on latency in between the countries. And what we found, 4 different clusters: northern, southern, eastern, and western. Well, you would say expected, right? Because this is kind of related to the geography. But no, we have some cases that are a bit weird, I would say. Here, for example, so we are talking about Western countries here. We see Mali, the big country in orange, which is clustered in the northern cluster instead of the Western cluster. So why is that? Difficult to know, but very recently we get some insight from AFPIF, where some people were actually mentioning that Mali, the telecommunication infrastructure is actually maintained by Morocco Telecom. So I would think that Morocco Telecom is also providing bandwidth and transit to Mali, and this is why Mali is actually clustered in the northern cluster. Madagascar and some other islands in the Indian Ocean clustered together with the northern cluster. Why is that the case? Would be interesting to know. I suspect that it could be relationships that they have with European providers. I know, for example, Orange is well established in Madagascar, and could be the same situation in other northern African countries as well. This is the case of Somalia. Somalia is clustered with Western African countries. So basically, it means that it is faster to send traffic from Somalia to, let's say, Nigeria instead of from Somalia to Egypt. So that's as well very weird. But we have two other cases which is those are actually completely weird. Like we have Ethiopia and Angola, two countries that couldn't be clustered. So if we had to make a map of countries, Ethiopia and Angola would be islands because they have no neighbors. They couldn't be clustered. And why is that the case? Ethiopia, for example, we see the latency to Europe is very, very high, 354 milliseconds. And all of their upstream providers are from overseas, or not local or regional. For Angola, 50% of the upstream providers are overseas as well. And what we also notice is that 16% of the trace route that we collected, the tracers were actually going through South Africa to Europe and then back to Angola. So that was a little bit of a loop. Now, if we push that a little bit further, we want to understand now what is the latency in between the clusters that we have actually found. So before getting there, what is the latency in the cluster itself? Eastern cluster and southern cluster is doing very well, so that's great to see. However, the western cluster, it means that countries in the western cluster, in between themselves, latency is quite high, 215 milliseconds on average. So this clearly gives us an indication that, okay, perhaps there need to be more intervention made in the western cluster there. Actually, it might be interesting for people that want to deploy, let's say, cache servers or things like that in those regions to serve countries in those regions to understand what are the dynamics in terms of peering and delay and etc. Now, we did a lot of pings to get the latency data. Now let's use the traceroute data to understand how our countries are connected in terms of upstream providers. So all the dots you see on the map here are upstream providers. You see, of course, a lot of dots in Africa and some of them in Europe and in the US. But from what we've actually gathered is that 38% of traceroute path, like the first AS hop, which is different from the original vantage point AS number, is actually found outside of Africa. That's quite scary, I would say. Out of this, 6.6% of traffic goes through South Africa and 4.5% through Mauritius. We were a little bit skeptical about this Mauritius thing. I guess it is because of geolocation issues. Mauritius, Wayok as a provider is located in Mauritius, so geolocations was sending us to there, but perhaps they most probably have infrastructure in Africa itself. And then we gather data on the centrality of those upstream providers. The more they are connected, the more they provide transit, the higher they will be on the list. So here you see the usual suspects: Cogent, Level 3, SECOM, etc. A few of them are Africans, and you also see Orange, which is quite high on the list. And from what we gathered, Orange serve almost 70% of all French-speaking countries in Western Africa. So is there something related to Orange, Western Africa? I don't know. We need to figure out. And then we also wanted to understand how many hops are there when the traffic leaves the vantage point to the target. For example, 50% have hops overseas, and we have seen that 14% of all the traces that we have at least 4+ hops in between before reaching the other endpoint. It means that, okay, the packet is going through a lot of hops. Perhaps there is some amount of traffic engineering that needs to be done in those cases. And then finally, what is the latency to the upstream providers? This could be interesting to understand as well. For example, we found that the northern cluster to North America is 71 milliseconds, and the southern cluster to North America is 227 milliseconds, so which is quite high. So basically, what the message we want to pass here is that if you have your upstream in the same cluster, latency is low, and if you have your upstream overseas, latency is higher, of course. Takeaways from this study, we have seen very well-performing countries: Benin, Egypt, Mauritius, Ivory Coast, South Africa, Reunion, and some badly performing countries which I guess would need more attention from the community of network engineers, IXPs, etc. Yeah, that's about it. And future work, we want to correlate this type of study with other factors such as physical infrastructure, IXP presence, peering relationships, and things like that. Thank you. This work is going to be published and presented at African in Cape Town, IEEE African in Cape Town. Thank you.
Thank you very much, Amreesh. Jan, if you can kick off the questions, please. Speak loudly, I'll repeat if it's off.
You can use your mic.
Yeah, you can.
Now it works. Okay. Hello, my name is Jan George. I presume that you did this stuff on IPv4.
Yes.
Okay. What would be the picture if you would start measuring IPv6? And what would be the difference in peering policies?
We haven't done the study on IPv6. That would be a good one to do, actually. The issue with that platform is only IPv4, which sucks. But yeah, we want to do that over IPv6. We'll find a way, whether it is through RIPE Atlas. But RIPE Atlas, as I said, there's too little alive on the continent to do a proper analysis. But we can try to do it.
Okay.
Yeah.
Just do it. Thank you.
Hi, Amreesh.
Hey.
Nishal. Firstly, well done. I thought this was really interesting. Good work, and we'd love to see more of it. My first point was going to be what Jan said. We'd like to see IPv6 data, even if it's not as complete as the V4 data set. I think it would be really good to show where people are doing well and people are not doing well. I wanted to comment on a few things. Firstly, the question you asked about Big Congo, the DRC. It's easier for example, Goma, which is closer to Rwanda, to get fiber into Rhinix, the exchange point in Kigali, than it is for them to go all the way down to Kinshasa. In fact, I don't think there's a fiber path down to Kinshasa as yet, so that might help. It's a difficult country to get fiber through, so that leads to what I'd like you to do next as part of your study, what I see as an extension, and not to limit it by geographic boundaries. And someone said it nicely this morning. She says, I'm I'm a citizen of the internet. I don't want to be limited by country boundaries. And while I understand why you do it, to me it makes a lot more sense to be able to do this on a per city basis, or on a sort of central kinds of cities. You know, I understand you can't go through all the cities in Africa. That would be a bit crazy. But for example, measuring data from Johannesburg to Botswana is a lot more interesting than measuring data from, say, Johannesburg to, or a lot different than measuring data from Johannesburg to Cape Town, which is a longer distance and, well, according to the laws of light, should be much further.
Yes.
And then as a further suggestion to this, I'm asking for a lot, I was wondering if you could do a similar thing with DNS. Measuring, for example, the topological spread of where country auth servers are based on information you have. And if you want to chat about it later, or your rest of your research team, I'm very happy to give you my ideas and suggestions.
Absolutely. Yeah.
But great work.
Thank you.
Hi, this is Alan Barrett. Amreesh, do you have any theories, ideas about why the latency looks as it does? I find it a little hard to understand, because I know the speed of light. Light travels like this far in 1 nanosecond, which means about 3 milliseconds for 1,000 kilometers. So how do you explain in-country latencies of hundreds of milliseconds? That's not enough for satellites, because a satellite round trip is about 500 milliseconds, and it's too long for terrestrial connectivity. So what's going on there? Is there buffer bloat slowing things down? Do you know what it is?
Could be there might be different reasons, right? It depends where the vantage points are situated. Are they in an eyeball network where bandwidth or something like that is being throttled? Are they going through some traffic engineering path which is not optimized, things like that? So we don't know. Those are things that eventually needs to be explored. Yeah.
Yeah, I'm not sure that other paths really explains it, because 100 milliseconds implies like 30,000 kilometers. Countries aren't that big. No matter how many circles you do round and round the country in a suboptimal fiber path, you're not easily going to get to 30,000 kilometers.
If I can add, I mean, in Africa we have so many different types of connectivity, and to add, we have so many salesmen of all kinds of devices that go in between the types of connectivity. So there's no doubt that additional devices add milliseconds and can add tens of milliseconds, firewalls and the like, and certainly wireless connections, whether they're fixed like wireless or not, can go through multiple paths and distances which, you know, each router that it goes through also slows down and adds a little bit of latency. I would suggest that in Africa we have very complex networks with multiple intermediaries which can always add latency, not just distance.
And Alan, I guess you're assuming that we are all using fiber.
Well, light and radio waves pretty much travel at the same speed. So no, I'm not assuming it's fiber. And Alan's right. There are certainly delays every time you go through a device, and that could explain some tens of milliseconds. But to me, it doesn't explain the hundreds of milliseconds.
Michukwi.
Amreesh, good job again. Just a question. Have you been able to factor in changes in the infrastructure connectivity between countries? So I'll give an example. I was recently in DRC, and I got to learn that despite the fact that they have access to the ACE cable, they are barely using it. And it's not because the ACE cable has cuts, it's because the cable between the landing station and Kinshasa, the capital, which is 600 kilometers, is so unstable that on certain months the uptime is about 45%. And the best month they've had was 85%. That's between January and July of this year. So primarily their main connectivity to the rest of the world is now on satellite, because the terrestrial path is just unreliable.
Stable. Okay.
So if you have a probe, for instance, in that country, 1 week of the month you probably have very good latencies, and the rest of the month it shows pretty high latencies. So was that something that you're able to factor in?
Not in this study, but what you commented is very important. For example, this is why we want people to install probes, and things like that can actually be revealed by proper internet measurements. So, but we haven't factored in things like unreliability of links in that study. Yeah.
Hi, Graham Benneker. I just wanted to comment on Alan's question. Where's he gone? He's hiding. Alan's question about the latencies and the high latencies. I think there is probably technology issues within the countries. Two things that I've seen. The first is that the 3G standards, so the mobile broadband standards, they tend to favor guaranteed delivery of packets over latency. So the 3G network will delay your packet for 3,000 milliseconds, but it'll guarantee that every single one will eventually arrive because it just resends and resends and resends until it's delivered. That is a flawed logic. I think anybody who's been involved in some of the buffer bloat and TCP optimization research will know that that's flawed, but that's unfortunately the way that the 3G networks have designed their protocols. So that contributes. And the other issue is, as Alan was alluding to, the buffer bloat issue. There's a lot of equipment in Africa that comes from a period where large buffers were put in, the implications of that wasn't fully understood, and that, along with the heavy oversubscription and running lines at 98%, 99%, contributes to a lot of queuing delay going through devices. So packets sitting in a buffer on a device for 200 or 300 milliseconds that are not gaining any benefits in being in those devices, but because of legacy configs and legacy ways of deploying equipment and architectures that are not properly understood and analyzed, we are seeing technical problems with the equipment.
Okay.
Good.
It's interesting.
It strikes me that Alan's 300 milliseconds is roughly the time it takes for light to hairpin through Europe and back. How sure are we that in-country is actually in-country?
How sure are we?
That in-country measurements are actually in-country and not hairpinning through Europe?
Because we analyze the traceroute data. The traceroute data, we could see that, yeah.
I've got a question, if I may, the last question. It seems like you struggled a little bit with the equipment. You mentioned you use speed checker, which not only limits to IPv4, but it also limits to Windows.
Yeah.
I've got nothing against Windows, but I think that it's a subset of our broader market.
Yeah.
And this question is leading to the RIPE devices RIPE probes that have been distributed, and you mentioned that there's a high density in South Africa, but largely on core networks and not at the end users, and a lack in the rest of Africa. Is that something which will be able to assist? I noticed there were a number of comments to bring in IPv6, and should we or could we get AFRINIC branded ones that might help to expand the footprint? I don't know if Alan wants to comment about that, but I certainly think that more probes around Africa will certainly help us to avoid any kind of proprietary softwares and proprietary platforms, and is in the interest of all the LIRs and regional and regional registry.
Yeah, most definitely. If we can take advantage of open platforms instead of proprietary paid platforms, that would be just better for internet research in general. But there was some discussion about rebranding the RIPE Atlas into AFRINIC, but I'm not sure how important that would be for the region.
Yeah. Hi, this is Alan Barrett. I heard my name mentioned, so I thought I should come here. Yes, indeed, there was a suggestion that AFRINIC could stick our logo on a RIPE Atlas probe. Personally, I don't really see the value of that. Everybody around the world knows the RIPE Atlas probes. so the compromise that we've reached is AFRINIC markets these things. We've got an AFRINIC branded fact sheet about why ripe atlas probes are good, but the probe itself is still branded with ripe atlas.
Are they cost effective? Is it easy to get access to them? Can we distribute them more widely to end users? Yes, please. Yes, I'll take 2 or 3, please. Yes. Okay, there's a man at the back there. His name's Nishal. I don't know how we're looking for time right now, but it's actually it happens to be the same person who's going to be speaking next.
Nishal, right?
Oh, is everyone rushing out for coffee? Have we got a coffee break? Okay, another question. Do we have more questions here?
Hi, my name's Fergus Mackay from Flex Optics. I'm a RIPE ambassador for the Atlas probes, and I've just bought a batch down for AFRINIC. There is a website within the Atlas pages that shows you all the events that people like me are going to be attending with probes. So you can see what events we're at and ask us for a probe when we're there. So they are freely available, and I try and carry as many as I can with me when I go to events. But there'll be people at various events. I'll be at AfricaCom, and I go to AFPIF and AIS, and probably here. So, aside from AFRINIC and Nishal, who also has stacks. So have a look there if you want them.
Excellent. Thank you very much.
And they are cost effective. The cost of using generic hardware is just way better than anything else you can do.
Fantastic. Thank you. Thank you very much. Okay, so there's no lack, and everybody's in agreement that the ripe atlas probes are the way to go if we're going to get more useful, more relevant information. I think we should all agree to work hard at getting more of these out there, especially at the end user points.
Yes. And maybe it would be good to mention that AFRINIC and ISOC are also sponsoring ripe atlas anchors, which are basically beefed up probes that could be installed, for example, at central locations such as IXPs or a main ISP. So AFRINIC is sponsoring, so please reach out to us on that.
Fantastic. Thank you so much, Amreesh. Well done. Very, very interesting.